Can you all hear me well? Good. All right, thank you. Hey, thanks for taking the time. I'll be here to talk about how us at Myntra, India's leading fashion e-commerce player, transformed its data lakehouse from V1 to lakehouse V2 that we call it. So before I get into it, I'd just like to um, explain a little bit about Myntra. Right. So Myntra is one of India's leading platforms for fashion brands. It's an e-commerce play. It's part of a larger Flipkart group. So Myntra brings together technology and fashion to create a delightful shopping experience for all our customers. It's our vision to democratize fashion using technology, and our mission is to help people look and feel good. So we work collaboratively with the entire fashion ecosystem, including our brand partners, delivery partners, artisans, and creators. So just to give you an idea of our scale, right? First off, I mean, we believe our true differentiator lies in our selection, our innovation, and our superlative customer experience. So in terms of selection, we offer 2.9 million styles across a wide range of 8,800 plus beauty and fashion brands, right? Um, we try to work towards bringing the best of trendy wear for Gen Z, or try to solve for the white space for teenager style needs, as well as look at things like sustainable initiatives by launching things like Myntra for Earth. In innovations like the foundation of our culture, right? Some of the most innovative solutions that have come out from Myntra have been vernacular search, My Fashion GPT, skin analyzer, and we've built out a lot of social commerce propositions as well to do social commerce too. And in terms of customer experience, it is our endeavor to provide a superlative pre and post purchase experience, right? So as you can see, I mean, we deliver across 19,000 plus pin codes in India. We've got 100 million plus app installs. Also, I mean, our user base, we are at around 60 million monthly active users on our platform. So I mean, technology is like at the core of the organization's fabric, right? So whether it be trend spotting as part of planning and design, or for discoverability on our app storefront, to enable brand enablement. Also, we use a lot of computer vision for our warehouse quality checks. Use a lot of ML for our overall smooth transition for the customer from pre to during the delivery stage. So as you can see, technology is deeply ingrained in our fabric, and it finds a place in the entire value chain. One of our recent launches has been Myntra My Fashion GPT and Maya. So this is us trying to do something with Gen AI and LLMs. The idea is to serve products that match the user's shopping intent within a chat interface. It kind of guides users to relevant products through natural conversation. It also understands these queries, bases natural language, right? Things for you want to shop for a particular occasion or a festival, or you want to look for styles, bases, movies or themes. So this kind of allows that to happen. This is something that we had recently launched, just to give you an idea in terms of what is the kind of technology that we generally play with. So, I mean, I just kind of walked you through the whole tech ecosystem at a very high level at Myntra, right? Just want to say, I mean, underpinning all of that is the need for a very strong data and ML platform, right? And that is what is going to ensure that there is timely delivery of quality data at the right time for the analyst community within the company, but as well as for integration with a lot of engineering systems across from storefront all the way to supply chain. So the data platform at Myntra, we call it MDP, Myntra Data Platform. And we have a set of guiding principles that we generally kind of adhere to. This is what we look at when we try to build out the data platform, right? So some of the things are data democracy. We would like data to be available to anyone, that should be a pretty seamless experience. It should be self-serve. So across the entire data ecosystem, all the way from ingestion to processing to serving, we want to make this a very self-serve experience across engineers, analysts, and other business stakeholders as well. The third thing is multi-tenancy. So in terms of understanding our overall resource utilization, etc., we want to bifurcate it in terms of different engineering departments or different analytics departments. So the need for multi-tenant systems is very important, and that's something as a platform that we try to build across all of our systems. Another thing is the ability to have multiple processing engines, right? So we have petabytes and petabytes of data on a lakehouse. We want to be able to bring in any kind of compute, right? It could be Spark, it could be Trino, anything to that effect, but make sure that the storage kind of stays independent. So then cost efficiency is really important on our side. We would like to crunch out the max in terms of both CPU, memory utilization, disk utilization. These are metrics that we consistently monitor and make sure our data pipelines also adhere to some of the guidelines that we have set. Security compliance is also very important. Even India is coming up with a new Data Privacy Act. So it's essential that we have data governance across the entire data platform, right? Discovery, data quality, and auto healing. Again, this falls under the data governance theme. I mean, discovery, data quality is pretty self-explanatory, but what we mean by auto healing is all of the pipelines are inherently idempotent. They have a backfill that can be run and things like that. So it should be able to recover from any failure. That is both from a batch and real-time streaming standpoint. I just wanted to give you a lay of the land before I get into what our previous architecture kind of looked like, and what some of our guiding principles are. So just to talk through what our daily statistics are like at the Myntra data platform. So we have around 1,000 data pipelines. We've got data in the tens of petabytes in a lakehouse. We have 80,000 user queries on a daily basis. Our clickstream pipeline, we do about 7 billion events in a day. In terms of users of the data platform, it stands at around 800, and that's just from an ad hoc querying, dashboarding standpoint. There are a lot of other systems that essentially integrate with the data platform, which I'll kind of talk about. We also have a lot of transactional ingestion, which does a lot of our operational analytics, right? So that is in the scales of tens of millions on a daily basis. In terms of use cases that are served off of the data platform at Myntra, we generally see 10% month-over-month growth. This could be coming out of new ML model deployments, you name it. I mean, there are new aggregates, new feature engineering pipelines. Net, we kind of see a 10% growth just in terms of use cases that are served. Right. So this is just how our previous architecture had looked like. So about a year back, right? This is how our architecture essentially was at the Myntra data platform. It's a traditional architecture that you just go read from left to right. I wish I had this. Let me see if this works. So but so we have multiple sources on the left, right? So we have the clickstream, which is the client events which are emitted through an SDK that's embedded in our app. We have a lot of the transactional ingestion that I was saying. We have a lot of MySQL sources, MongoDB sources, etc., which we ingest from. So we use Debezium, we use Kafka. That's like the entry point for everything into the data platform. And after that, we have a bunch of, there's a Kafka Connect, in-house inbuilt Kafka Connect connector that we had built that essentially reads from Kafka and just lands it onto Azure Blob. And from the transactional ingestion on the top side that you see, we are essentially deduplicating all of the transactional ingestion, the CDC events that we get from MySQL. So all of this finally landed as ORC files on our lakehouse. So this is what we call Lakehouse V1. right? And so they all used to land as ORC files, and most of them were Hive managed tables. And at the top, you can see that we have a lot of batch processing jobs that run on Spark, and on a use case basis, sometimes we use Trino, but that's mostly for querying. And on the serving side, we have Trino, which is based on Hive Metastore, trying to read a lot of these Hive managed tables. That is fronted by a serving gateway, which then we have consumer applications on the right side. We use Superset for certain engineering metrics. We have Power BI that we use for business dashboards and revenue metrics, etc. We also have an in-house platform that we built called UDP. And that's a React.js based application. Again, that has a lot of important critical dashboards that are important to company. And there was a data warehouse that is there as well. So it was kind of like a weird setup. So we had some aggregates that were still running on a data warehouse down below. The processing and the serving was out of the data warehouse, while there was another set of aggregates that were completely being run on Spark. I just kind of covered what the batch side of the equation looks like. At the bottom, we have a whole real-time pipeline. Like I said, we have a lot of integrations with other storefront engineering systems. So essentially, we take in all that clickstream pipeline, which I said is in the order of billions of events per day. On a real-time fashion, we have two mechanisms of consumption, right? So there would be things like low latency aggregates where you want to see click-through rate or the orders per minute, etc. on a real-time basis. So we get that landed onto Druid. But we also use Spark streaming to do a lot of real-time feature engineering. Essentially, we want to create vectors, store that in an in-memory data store, and then have that served for other recommendation or personalization models that are residing on the storefront side, right? So that's why, I mean, the data platform, like I said, it encompasses, it plays a big part in a lot of things, from influencing the user path on the Myntra app, while also serving out a lot of aggregates and things like that that are critical for reporting, right? And so some of the challenges that we had, right, is, so like I said, we were using Hive Acid, and there were some issues that, not some of this, something that consistently kept happening is, there would be this asynchronous locking of files when we are trying to do a write, and we run compaction jobs that are independent. This essentially ends up locking files, and it used to cause failures as well in terms of the Spark jobs, and our jobs would have to go into many retries. Another thing that some inefficiencies that we saw is, like I said, there's a data warehouse which used to house some important aggregates. And what we essentially used to do is just reverse sync from the data warehouse back into the lake house, right? So that there's just a unified way for all of our consumers to read those aggregates. But what it was essentially causing was duplicate sources of truth, right? And there could be failures in terms of that reverse sync process as well. And in terms of management of the entire lakehouse, because like I said, there are multiple file formats, and Spark's support for the Hive connector so this was on Spark 2.4. The support for that kind of pretty much ended, the one that we had, the Hive Acid connector. And so these were some of the challenges that we had in our previous architecture. And I'm just going to walk you through how we kind of transform this in the course of 8 to 9 months. Right, so like we took a step back, and we were kind of thinking, what is important for us, right? What is it that drives us to seek change, right? So, platform scalability was very important. As the data keeps growing, we wanted to make sure the compute non-linearly grows with the storage, right? That was really critical to us. Time to market in terms of, reducing our overall SLAs of our aggregates, right? Or reducing even the ability to create a job for any analyst or engineer in the company. Our total cost of ownership should essentially come down. This is a bunch of factors, both in terms of infrastructure cost reduction, but also in terms of developer productivity. We wanted to enhance the collaboration across data teams. Like I said, we have a large data science team, a large analyst team. We want to ensure that all these data sets could be efficiently shared between all of these different teams, right? So that we don't end up having teams creating duplicate kind of data sets. So what we did is we kind of saw that Delta Lake was providing us a lot of capabilities. So one was the protocol standardization, right? So now with the Delta kernel, etc., there are use case specific engines or connectors, like for Databricks or for DB-SQL or for Trino, right? So it can be used for I/O, but there is seamless interoperability um, for different compute engines. The second thing is, like I was saying, we wanted to reduce our overall SLAs, wanted to start moving towards a more kappa-based architecture. And again, Spark 3 with Delta Lake kind of unifies the semantics between batch and stream. So that was another thing that was under consideration. There's a lot of new features that come with these, with the new Delta table format. ACID, versioning, auto compaction, etc. These were really critical to us because, like I said, we were having a lot of challenges with the Hive ACID tables and the asynchronous compactions that we were doing. Data storage optimization was another big one. While we moved to Delta Lake, we implemented a new compression called Z standard, and we saw that that gave us around 35% reduction in our overall storage as well as costs. So when we did this couple of POCs with Delta Lake, that's something that we noticed. The other thing is with Delta, there's very aggressive metadata and stats that are collected. What that essentially allows you to do is on the Trino side particularly, it allowed for a lot of push down optimization. So a lot of filters, etc., could be pushed down to the query engine. And thus, both from a storage standpoint, it helps reduce storage, but also queries were starting to run much faster as a result of this. Definitely open source support was very important for us. As you could see from our previous architecture, we have a mix of a lot of platform offerings as well as a lot of open source software as well, right? So our redesigned architecture, so we were able to pull this whole project off in 9 months with the help of the Databricks team, right? And what you can see is while most of the stuff on the left side have stayed the same, we have now been able to get Spark streaming. We've switched to a medallion architecture in the middle, with the traditional, bronze, silver, gold. Make sure all of our raw data lands in a bronze layer. We switched to ADLS Gen 2. That in itself gave us a lot of improvements in terms of list operations, etc. We were able to switch to Spark streaming to allow for more real-time ingestion into the data lake. The Spark and Trino still stay the same, but at least now they are working off of a single Delta Lake format. We still continue to use a Hive metastore. And then on the real-time side, there have not been much changes, but one thing that we're going to look to do is bring real-time analytics on Delta Lake, right, with Delta tables. So that's another thing that we're kind of essentially exploring. But a lot of the challenges that we faced, it kind of got done away with because of this, right? Some of the main things is, like I was saying earlier, there was a deduplication process from the ingestion to the data lake, right? And this we were able to reduce 40 to 45% of overall ingestion time, right? And then also, because we were able to standardize on this Delta format from a data governance standpoint, it allows us to have a uniform auth and Z across Spark and Trino as well, right? And I think, yeah. So some of the business outcomes that we had, I mean, with this whole change, we've had a 25% performance improvement in terms of our real-time pipelines. like I was saying, when we switched to Spark 3 with the streaming, there was a lot of compression that had gotten in on the streaming job as well. That helped reduce our end-to-end latencies of a streaming job. So that essentially helps in faster in-session personalized recommendations. In terms of our overall infrastructure cost reduction, we saw a 35% cost reduction rate. Like I said, one big factor of that was the ingestion. Essentially, we could do away with a very large Hive cluster, which was doing a lot of compaction. And because of merge on read that is there on Delta, we were able to exclude that cluster. But also, a lot of our old batch processing jobs, we generally saw around a 30 to 35% reduction in the overall job execution time, and hence the cost as well with Databricks. So I think that's pretty much it. Thanks for listening in. You can find out more about what we do at Myntra Engineering here at this blog. Happy to take any questions.